Thank you very much. I'm really glad to be here and to be able to talk about Lithium. So I started Lithium about a year ago now for my master project at EPFL. And so Lithium is, as the name says here, a split-brain resolver for Akka-Cluster. So first, I'm going to start and kind of explain some things about Akka-Cluster that we need to know for the rest of the presentation. So Akka-Cluster is a way, so for instance, you have your active system and it's running on one computer, and maybe the computer is not fast enough and you want to scale horizontally, and that's something you can do with Akka-Cluster. So you can have multiple active systems connected together over the network. So you can create a distributed, distribute your work. So, but now since we have multiple active systems working together, and to be able to work together, they all have to keep track of who is part of the cluster. So keep track of the membership. So each node in a cluster can be in any of those states. So joining, up, leaving, etc. Then there's one of the nodes will be kind of elected as a leader. So there's no leader election per se. So the way it works is that since every node keeps track of the membership, so they know who is part of the cluster, and then they take the kind of they order in some way all the cluster members, and they pick the first one with bias towards up and leaving members. And so what that leader does, so it takes care of shifting nodes in and out of the cluster. And it does that when there's convergence. So convergence meaning that when he sees that every node has kind of observed the same membership, then he can kind of upgrade a node that wanted to go in the next step. So for instance, a node can at any time join the cluster. He'll arrive in the joining state. When every node will have seen him as joining, the leader will move him as up. Here I've up and leaving are a bit special because those are the two only states that are kind of fully fledged members. So for instance, your cluster singletons or shards can only run on nodes that are in these states. And this is a bit important. This is quite important. So additionally to knowing who's part of the cluster, you also have to know which nodes are reachable and unreachable. So how that works, so this is very simplified. So here we have node 1, which is the observer of node 3 that will ping him. And then rather quickly, if node 3 is alive, node 3 will respond back, and node 1 will say, okay, well, he is reachable, and he will then gossip that out through the rest, telling, okay, well, I've seen him as reachable. But what can also happen is that a few seconds later, so here a few seconds kind of could depend on what you're running. If it's like a very good link, it should not be it could be a few seconds, but if it's a very bad link, maybe a bit more. But then, so what happens? So node 1 will ping node 3, and a few seconds later, no answer. And well, now node 1 though knows that node 3 is unreachable, but unreachable doesn't mean much because you actually don't know if the node maybe he crashed and that's why he didn't answer. Maybe he's having a very long GC pause, and that's why. Or there could be a network issue, and it could be kind of completely working well, but just on the other side of network partition. So as a net on a network partition. So meaning that when a node is detected as unreachable in Akka or in any an Akka, you don't know if the node is alive or not. You just know he's not there to answer your call. And so what this means is, so as before, the leader moves one state to the other one on convergence, but you cannot reach convergence when you have those unreachable nodes because you're never sure. Maybe the node is not one of the nodes. You're still waiting for the convergence of one node to kind of converge. And he's unreachable, but you can't ignore it because maybe he's not dead. He might come back, and then kind of you figure out that, oh no, there wasn't any convergence, and I moved node to a next state, and then you can start having problems. And so what this whole thing then means is that if you have one node that's unreachable, that maybe because there's that node, it has crashed or there's a network partition, you cannot add new fully fledged members to the cluster anymore. Some nodes might still join, but they don't really take part in most of the kind of cluster tasks. And then the leader will never move them to up. So this is kind of a bad situation. So we have this cluster here. This is the base cluster I'll use as an example for the rest of the presentation. So we have a 5-node cluster. We have one like super important singleton here, node 4, that does something important. I don't know what. And we have 3 sharded entities, Alice, Bob, and Charlie, that represent the user. Could be I don't know, their bank account or kind of some user information or anything. So you have running this in production and you're happy and it's going well. Then one day at night, something goes wrong, and all the nodes in partition 1 will detect the nodes in partition 2 as unreachable, and vice versa. Partition 2 will detect the nodes in partition 1 as unreachable. So now you have a network partition, or technically you don't even know if it's a network partition. Maybe the other side is dead. Who knows? So for your business, what this means is if you have a request that gets routed like to one of these nodes, they will all fail if they try to reach the singleton, or if it maybe was a request for Charlie, and the other side also. So now you have your some of your users might get started, might see problems in the app, some don't, and like they refresh, one time it works, the other time it doesn't. So now let's see. Okay, you want to fix this. I mean, it has to be fixed. Your app has to be up, completely up. So let's see what not to do. So you went through Akka's documentation and you see, oh, well, if I have an unreachable node and I down it, it will be automatically removed from the membership, and then Convergence will be reached and everybody's happy. Because then Akka will start migrating, we'll see, oh, well, there's a singleton missing on our side, let's start it up there, and same for Charlie. And so you do this parametrically, for instance, here by just calling a cluster.down and the address of nodes that you want down. So you see that, well, let's try what happens. So let's do that first with partition 1. So partition 1, we'll decide to just down the other side, forgetting about them. From their point of view now, the other side is gone. There are no reachable nodes anymore. And we'll start up the missing shard, Charlie, and the singleton on our side, and everything is well. You have a bit less nodes, but now you can at least start adding nodes to the cluster again. On the other side, your node 4 and 5 will do the same thing, because actually they weren't there. There was really a network partition. And so what happens here? Same story. Forget about the other side. Convergence is reached. Unreachable nodes are gone. And so shards and everything get started on their side. But what happens in reality is that now this kind of one cluster gets split off in 2 different clusters, because this side doesn't know anything anymore about node 1, 2, and 3. They're kind of they remove them from their membership, and same for the other side. And what we have now is called a split brain. So if your cluster that got split into 2 different clusters, they will do the same thing in parallel. And when you get in this state, you will then really start getting problems. You'll start corrupting your data, your state. And yeah, that's if you have this, everybody will be running around. So this is why you shouldn't do this. You shouldn't just down the unreachable nodes. So now, what should we do? So one of the things you can do is use a split brain resolver. So what the split brain resolver does, and it's kind of a misnomer, it prevents split brains from happening in the first place. So what it will do, and it will pick at most one, or like at most one partition that will survive. So in the case we had before, the split brain, actually two partitions were picked to survive. So the survivor partition will down the unreachable nodes, just scratch them off from its membership. But then, to make this safe, the survivors on the other, the non-survivors, sorry, on the other side, will just kill themselves. They will just shoot themselves in the head. And this will done following a strategy. So strategy is how this surviving, non-surviving partitions are picked. So Lithium is one of the split brain resolvers. So it's open. So it's an open source split brain resolver. It can provide you 4 different strategies to use. I'll explain them later. And it's also, to my knowledge, from the open source ones, it's the only one that supports multi-data center clusters. So there are existing solutions. So you might have, and you probably have heard of the Lightband split brain resolver, which has one more strategy. The 4 first ones are the same. That has multi-data center support. And so one of the reasons why I developed one is that it's fairly costly. And most smaller companies, I don't think they can pay for it. But yeah. Then there are 4 other ones I found on GitHub. 2. So I found one blog post about one that has been used in production, and another one that last year at Scalar Days I heard was used during presentation at Moya. And interestingly, those 2 ones that are used in production, is at least one. I'm pretty sure it still is. Has only one single strategy, so they're very simple. They're kind of they give you the simplest strategy. Then there are 2 other ones that have multiple strategies, but as I'll show at the end of the presentation, they actually fail all the tests I've written. So how does Lithium run on your cluster? So Akka provides you this abstract class Downing provider that you have to implement, and that then will provide the actor that will do this split brain resolver stuff. And so this actor will be instantiated by Akka on every node of the cluster. So it's not, at least in the case of Lithium, it's not like only running like on like one of the nodes as a singleton or as some additional node in the cluster. So it's really everywhere and like on every node. And then very roughly, it does some stuff, and at the end there's a strategy. So this is a trait from Lithium that, given a worldview, which is a enhanced membership with a bit more information, as we'll see later again, why we need that additional information, and given that, give you back a decision. In reality, so it will be only the current leader that will take the decision will take action on the decision. The other ones just passively do their stuff, and when the leader changes, the new leader can directly take over. Setting it up on your cluster is actually is super easy. So it's only configuration. So there's some auto-magic stuff where you give here the concrete instance of your Downing provider. The Downing provider will get instantiated, and then you simply add the configuration with strategy you want to use, and some details on some other configurations about that strategy. And it is technically all you need to try it out. No. So you still have to choose a strategy. So now we'll go into the 4 different strategies that Lithium can provide you. So I use the same names as the Lightband one, because I don't think it's a good idea to just, for the sake of changing names, just change name for the sake of it. And so you can technically kind of use both documentations. So first, keep majority. Keep majority, as the name suggests, will pick the partition that has the majority of nodes in the cluster to survive. So how does this work? So in this case, well, we'll see here, this one partition, well, we'll call this partition 1, has the majority, 3 out of 5. So that side will decide to survive, start up the shards and everything, and the other side, around the same time, will decide to down themselves. So now we have only one. And we're fine with like everything's fine. You can start adding new nodes and everything to your cluster. So it has a few, it has downsides. So it can happen that your 5-node cluster might be split into 3 partitions, 2, 2, and 1, for instance. And so what this means is there no partition has a majority, and it will end up downing your whole cluster because no one will actually decide to survive. Because imagine with the 3 partitions, from the point of view of one partition, it doesn't know if there are 2 on the others, if they're on the other side, if there are 2 partitions or only 1. So in this case, no one will decide to survive. Then there's a kind of variation of keep majority, where you can decide what this majority was, so what the quorum is you need, so that what the quorum is. So this is useful if you have a fixed size cluster, and with this you avoid some issues that can happen where both sides maybe don't. In keep majority, you can have an issue potentially where both sides don't count the same number of nodes on each side, and in very rare occasions could lead to a split brain happening. So this one is, well, basically the same as before. This side will survive, this one will down themselves, as we see here. This has, again, the same type of downsides. So like you have nodes that for some, you have nodes that left the cluster, and then you have a problem. You have less than n nodes. No one will decide. No one can no partition has the quorum. Your cluster might down itself. Same happens also if none has at least. So if you have too many partitions, and then as a to keep the safety property of not creating split brains. If and this is mostly if you have this issue, you should use keep majority. If you have more than 2n-1 nodes, where n is the quorum, like all the nodes would down themselves. So this, as an example, how what could be: you have your 5-node cluster, and you do an update, and you don't do a rolling update 1 by 1, replacing 1 node and 1 node, but you start up all 5, and at one point you have 10 nodes in your cluster. Your quorum is 3. And then if you have a partition, 2 sides could technically reach the core, have the quorum, and 2 could decide to survive. So with doing this, you'd never have this issue, but it will log you a warning, and if anything happens, just like the whole cluster will down itself, just to be sure. And as I said before, because the number of nodes is statically known, this cannot by construction lead to a split brain. So now we have the 2 next ones are kind of a different breed of strategies. So the first 2 ones rely on counts. These ones rely on kind of one single node, like one important node in your cluster. So here, keep oldest is they will pick the partition that has the oldest node. So this is interesting if you because the oldest nodes are the ones on which the singleton instances are running. And so if you have a singleton that you, if a singleton is gone, and if it's often used, you don't want it to be gone. So you don't want to kind of, if there's an issue, you want to have, don't want to restart it. This is an interesting one. So here in this case, we have node 1, which is the oldest, because we know that because here the singleton is running here. And this time it's the bottom partition that will decide to survive. And the other one, because they cannot reach the oldest node, because they see it as unreachable, will simply kill themselves. So what can happen is, so your oldest node crashes or gets cut off from the rest of the cluster. And with this strategy, what will happen is that like the many will actually, so your 100 node cluster, and you have that one oldest node dies, and now you have 99 other ones that down themselves, and your whole cluster goes with it. So you can, in case you don't want that happening, so this kind of extreme situation, you can configure saying that if the oldest is seen as alone, then he won't survive, then it's the other ones that will survive. Finally, keep her free. So keep her free is kind of the equivalent of static quorum, where now it's a node that you configure that will be the one that will survive. So in this case, we would have configured, so you configure in configuration, you give the address of the node, and you would have given the address of node 5. And so this partition is, they can reach node 5, it's here. This side will survive. Oh, this side will survive, and the other one will kill itself. It has the same issues as the keep oldest. If the referee now is alone, the whole cluster can come down with it, just pull everyone with him. And so you can also configure that so that doesn't happen. And again, this one also, because it's statically known who the referee is, so you can have like, as before, when you keep oldest, like sometimes your two partitions could technically think like see two different oldest nodes, because he thinks the real oldest one is dead, or his line is not dead, but has left the cluster. But so this one cannot lead to a split break because everything is statically known. So here's a real small decision tree to help you kind of decide on how to choose. But what to want to choose? So there's one little trick. So in Akka, you can tag your nodes with a role. So if you have some stateful nodes, you tag them with some role, I don't know, VIP, whatever. And you have a like worker nodes that get spawned on demand. At first you would think, okay, well, my cluster has size is dynamic, so I have to use keep majority and have that tiny chance that it could lead to the split break could happen. How can I use static core? Well, you can use this role. So you can say to Lithium which roles to take into account. So this says, okay, these are the only nodes that are really important in my cluster. So the VIP nodes, VIP ones in this case, because you don't care about workers being downed and restarted. They're made for that. So then in that case, you can use static quorum. So, so this was a quick introduction of Lithium and just like kind of an overview. Now I want to go into the kind of the edge cases. So you can very quickly, for 95% of the kind of scenarios happening, you're fine if you don't really think about the edge cases. However, for the last 5%, and to make this like production ready and so that I'm able to sleep at night, we have to think about the edge cases that can happen. So I'll talk about 3 different ones. So the indirectly connected nodes. So here what we have is a cluster where we have some kind of, we don't have a clean network partition. So only the link between node 2 and node 4 is broken for some reason. And what will happen is that node 2 will observe node 4 as unreachable. And since that information will be gossiped out. And there's this strange thing where, which kind of makes sense, but when node 2 will tell node 1 and everyone that node 4 is unreachable, they will actually believe him. Node 4 will do the same thing and detect node 2 as unreachable, node 2 as unreachable, and then gossip it out again. The only thing, what's not happening is that when a node sees an unreachability detection of itself, it won't believe it. So we have this here, and I'll show you a scenario how this can lead to a split brain if you're using, for instance, the keep oldest strategy with the down oldest if alone configuration. So let's go first over who the leaders are in the cluster. So we have this order. So the ordering is as this. Node 2, there's a preference for node 2, then node 4, then node 1 as a leader. So node 2, node 2 will be a leader here. Will be the leader of itself, because from the point, like, no one else can reach him, because, well, this one is detected as unreachable and has like kind of lied to everyone about it. So all these nodes here, 1, 3, and 5, will pick node 1 as their leader, because they can't reach node 4. And finally, node 4 is the leader of itself, because he can't reach node 2. And node 4, there's a preference for node 4 over node 1. So we have, in this case, we actually have 3 leaders in the cluster. So 3 points where decisions are taken, or like the action is taken on nodes 2 down. So, and node 2 is the oldest node in the cluster. So let's start. So let's start from the point of view of leader of the leader on node 1, the leader here. So for them, they can only reach 1, from what they think, can only reach 1, 3, and 5. Then we have, from the point of view of node 2, node 2 can reach 1, 3, and 5, but also itself. So 1, 2, 3, 5. So we have this partition here, as seen by this node. And finally, node 4 that can reach 1, 3, 5. And itself. So we have this partition here. So we have, these are the, like, this is how the cluster is seen by every kind of non-clean partition. So let's see what happens. So the leader node 1 will decide that his partition has to down itself, because, well, it cannot reach the oldest. It's not part, node 2 is not part of this. And because it says down the oldest if alone, well, no, from his point of view, he's probably not alone, because they cannot reach also node 4. So they don't. This is a case where they kind of assume they're together, but they're not. So 1, 3, 5 will down themselves. Then we have node 2. So the leader here is this side, will decide to survive, because, well, he is the oldest and he's not alone. So he and his buddies here, what he thinks are his buddies, decide to survive and will down node 4 only. And then finally, node 4. So this partition, as seen by this leader, will decide to survive, because in this case, the only one he can't reach is the oldest node. The oldest node is alone, and you have to down it. So this one would just down node. And now if you're unlucky, and first this partition, because everything happens asynchronously, kind of around the same time, but asynchronously, this side will decide to down themselves first, and then these two will decide to survive, and there's no way that information can so yeah, if that happens, so this one downs himself, and then the 2 other sides survive, you end up actually with a split brain. So let's see how we can how this is avoided from happening. So nodes, we say nodes are indirectly connected when a node has seen his own unreachability detection. So you can see that because when messages, the detection is gossiped out, you can see who has seen it. And so from that, you can infer if a node is indirectly connected. And then also by kind of symmetry, the one that observed also that node is unreachable will also be tagged as indirectly connected. And then what will happen? Lithium will handle these so now we don't have only reachable and unreachable nodes, we also have indirectly connected nodes, and the indirectly connected nodes will be handled differently and be automatically downed. So these kind of split brains cannot happen anymore. Now, unstable cluster views. So what I haven't said before is that when a unreachable node is detected, so potentially like an issue in the network has been, or crash has been detected, each side will wait until their view of the cluster stabilizes, so it's stable for long enough. The reason for that is maybe, well, it might be just a transient change, so it might node just wasn't reachable and just come quickly back up. So you can avoid by downing those just by waiting. But more importantly, so that there's no decision taken on a kind of partially final state. So what we have here is this side, nodes 4 and 5 have an issue. For some reason, they see the cluster, like the membership state, for some reason keeps changing. And so they keep pushing down the line, like when to take a decision, because you shouldn't take because they have learned not take a decision without really waiting. And node 2 and 3 don't have that issue. And they that don't have that issue, and they will we'll look at their point of view. They will quickly read that kind of stability period. So here we're using key majority. And they will decide to survive and down the unreachable node, so forgetting about them. And then after some time, start up the singleton on their side and continued working. But what actually was happening on the other side is, so there's a contract normally that the non-surviving partitions have to kill themselves, but here they didn't kill themselves yet because they're still waiting for the stability. And the singleton has already been started on the other side. I mean, there's no way of knowing what happens on the other side. So like it just waits kind of long enough, but here not long enough. So here node 4 and 5 still waiting. And you have a split brain, at least for some time, until it becomes stable, and that side will downs itself. So the way this is solved is, at the first occurrence of a issue in a cluster, a timer is started. And the timer, what it will say is, so if the timer gets hit, that means that's the earliest time, is like a bit before the earliest time a partition on the other side might have finished this like decision taking, survived, and starting up the singleton, the shards, and everything. And so when the timer is hit, so this will get hit here on the unstable side, and that partition, just without even looking at the worldview, looking maybe I should survive, maybe I shouldn't, will just automatically down itself. And so this way we don't have that issue. And at the same time, it's probably, if you have these kinds of things happening, there might be some networking issue, and it's good to kind of restart and hope your nodes get moved to a different place where you don't have these issues. And finally, status changes during partitions, and this is the most ugly one of them all. So here I've added some additional information. So at the moment, we have this cluster, there's convergence on the membership, and everyone sees the nodes in D state. So everyone up, but just node 2 and node 3 that just joined the cluster and are in the joining state. And node 1 is the leader. What will happen here is that, okay, there is convergence, the leader sees it and will move these nodes 2 and 3 to up. But exactly at the same time, there's network partition happening here. And so this will happen. So when the leader will gossip out the new state of nodes 2 and the updated state with node 2 and 3 up, that information will never arrive to the other side. So from the point of view of partition 1, from everyone here is up, and node 4 or 5 is still up. So when this network partition happens, if you're using key majority, partition 1 here will decide to survive because, well, 3 nodes, 2 nodes on the side. Yep, it's a majority. I survive. But what's happening on the other side? The 2 nodes are still in the joining, as seen as in the joining state, because the updated membership as sent by the leader didn't arrive to any of the other nodes in time. And here what will happen is that partition, this one, bottom partition number 2, will also decide to survive. So because joining nodes are not counted, because I explained at the beginning, nodes can always join the cluster. Like when there's a network, at any time can join the cluster, but just not move to the up state where they can really take part of the cluster tasks and like hosting shards and everything. So this here, they will decide to survive because, like, well, we're 2, it's 1 on the other side, we're a majority. So this side decides to survive, and the other one decides to survive. You have a split brain. So the way this is solved is by always assuming that the nodes on the other side move from joining to up. So it's kind of a pessimistic assumption, but you don't have really much of a choice. And so what this happens here, by assuming that they will see, oh, we're not a majority. We're to the other side of 3. We're not the majority here. There's the same kind of story when nodes are leaving the cluster, but just the other way around. So this is when this gets solved. So finally, quickly, kind of the architecture of Lithium, because now we kind of understand the little things it has to do. So there's the kind of split brain resolver is the actor doing kind of the real work. So downing the nodes. This one will listen to events from a split brain reporter that reports on split brains happening. So this one holds the different timers, waiting until the cluster is stable. When this detected that the cluster is unstable, or at least the partition is unstable. And this one takes information from like the cluster membership events and from this here, the reachability report. So the reachability report is the one that's provide this additional reachability event, so the indirectly connected nodes, and it does that by listening, like cluster membership events or the reachability events from Akka and everything, mash them together and gives this enhanced information to it. So, well, it's good to know about issues, but it's like not issues, but it's good to know about things you have to solve. But it's better to have tests. So about 70% of the code base are tests. That's the part that takes the most amount of time, and I think it's the most important part because it has such an important status in the cluster, because if Lithium does something wrong, it'll just take everything with it. So they're quite a collection of unit and property-based tests. The property-based tests are tests where you kind of randomly generate test cases. So what I did is I generate kind of scenarios, different worldviews. And then you kind of simulate network partitions, and you just throw like thousands and even millions of different scenarios on the strategies, and checking that's only one that will decide to survive. So this is one that's very useful, but because it's impossible to simulate all the kind of little nitty-gritty details of Akka, there are also multi-node tests that take some time to run, because I didn't implement them very well, but yeah. And finally, we have been using this as Swissborg in production since a few months. We didn't have any safety issues, so we'll never create the split brains. We figure out some bugs, for instance, in some cases there were some issues, but we saw Lithium went a bit trigger happy. That got resolved, and so now it's going fine since at least a month now, which is very nice, and that's why I can sleep at night. So finally, a quick comparison, because I don't have much time anymore, with the other Speedburn resolvers. So here I only have the open source ones. I didn't have any occasion to look into the Lightband one. I didn't have any access to it, so I can only show this. So this I was able to run run the multi-JVM tests on different Speedburn resolvers, and then for each different strategy. And so we can see that, so this one and this one are the two that I've found that they were used in production. They passed the test. They're the simplest one, only implementing static worm. And then the two other ones that are fairly complicated fail all of them. Mostly they fail all of them because they don't handle indirectly connected nodes. And also because different strategy, maybe there's the tests kind of expect the scenarios to be resolved in a kind of specific way, and that's specific to Lithium, and that might not be exactly how they do it. So there might be some false positives in my test. But this gives like an idea, gives you kind of quick comparison. So it's good seeing that the production ones are at least passing the tests. So we reached the end. So we've seen how to start with Lithium, how to try it out, but also seen like what the little things it does more, what you don't expect when starting to develop a Speedburn resolver. So that was the hardest part, and still is, and that's why the project is not like 200 lines of code, but a few thousand, just because of that. I hope you were. I hope you liked it and you want to try out Lithium. Here's the link. Contact me, and if you have any questions, I think now's the time. Thank you much.
All right. Thanks, Dennis. Thanks for this great, knowledgeable talk. I believe everyone has enjoyed it. So, meanwhile, we've had one question from Rafał Piotrowski. He asked about what was the fifth strategy that is present in Lightband Speedburn resolver and not yet in Lithium. Do you know that?
Yeah. So the strategy, I don't remember the name, but it relies on Kubernetes to provide some kind of lock. So it uses the Kubernetes API to so that only one partition, like there's only one partition that will be able to take that lock, which is pretty interesting because it relies on something external to the cluster. I've been thinking of adding it. I just didn't have the time. Not that enough knowledge on Kubernetes to do it quickly. But yeah, that's the additional one. So one that relies on something external to your cluster.
All right. Thank you. So if there are no more questions, we would like to invite you for a Q&A session with Dennis, to which you will find the link on Hopin. And now we will have a short break, and after we will come back with another talk. Thank you, Dennis.
Thank you. Bye-bye.